That should be okay. Okay, so I will just now send the PDF.
Excuse me, sir.
Yeah.
Sir, instead of me, I think you can send the PDF to Dr. Professor Badul. He is the one who is chairing the session.
Okay.
Is it possible?
Sure, sure.
Yes, sir.
That's easy to do. Hold on. Let me make sure. Yeah, let's see. Well, it was here, so it must be here somewhere. You know, there's so many of these things that it should be on desktop. Ah, here it is. Let's see, make sure it's the right one. Okay, it should be on its way. Hold on. Yeah, so I have sent it to Bahadur, and hopefully he will receive it in a minute. I don't know.
Yeah, sure. No.
Oh, Bahadur, did you get that?
Yeah, I'm just looking over it. Not yet, but it may be synchronizing. So.
Oh, okay. So it has reached you at least. Something has reached you. Yeah, I don't know. Usually this Zoom is quite robust, but for some reason today it doesn't want to show the presentation.
That's strange. I received the file, but I mean, okay, because it's better if it's from your desktop, but I will share it from here. I mean,
Oh, if it's more or less okay, it's okay, you know, so long as it's more or less okay. It could be, you know, some settings on your computer or something.
yeah, okay. Yeah, so what bit?
I'll be right back. Just 30 seconds.
Okay, so Professor Vansal, I just share my screen.
Looks okay. It looks okay, Bahadur. Thank you. I'm not sure what I would do with this without it.
I can just move it forward and back. So
can I move it? I don't think so.
no.
Which is okay. I think
let me give you my desktop control. Just a minute, if I can. I mean, I think this thing one can give it. So let me try that first.
it's quite okay. I can just tell you next slide. That's also okay.
Okay, sure.
Yeah, let's not try anything fancy. This will crash.
Yeah. So actually, we can start in 2 minutes or so. So
anytime.
and thank you for taking this midnight talk.
No, well, that I'm up pretty late usually, so it's quite okay. It's actually very convenient because it doesn't interfere with anything. It's this way. It kind of. Otherwise, you have to worry about schedules and so on much more. So, so is it all online, or are there people sitting in some room as well?
It's all online, actually.
Sir, actually, there are supposed to be 160 participants, and I think more participants will join. And also, it is being live streamed in our institution YouTube channel. So hopefully they will join. Some are still joining.
Yeah.
The program is supposed to start at 10. Yeah.
Sure. We can wait a few minutes. That's okay.
Uh,
If possible, I would appreciate if it is not recorded, although I don't know if that is possible. It's just that there's so much stuff on the web these days that I have been discouraging too much more to be added there. But if it's impossible for you to control it, then that's okay.
okay, sir. Yeah, we'll.
Thank you.
Yeah.
So Bahadur, are you in Mumbai still, or are you at home?
No, I'm at Mumbai. Yeah. Okay, so it's 10 and we have 40 participants on Zoom. So Divya and others, please let me know. I can start now, and Professor Vansal is ready. I can start. So
Anytime.
okay, so we can start with the other schedule is there. So a very warm welcome to you all on the second day of first international conference on material science and applied physics, organized by Department of Physics, Panchunga College of Mizoram University. This is Bahadur Singh from TFR Mumbai. It is my great privilege to welcome today's keynote speaker, Professor Arun Bansal from Northeastern University, Boston. Of course, Professor Vansal doesn't require any introduction to all of us, but it's nice to go over briefly on his research career. Professor Arun Bansal currently is a University Distinguished Professor of Physics at Northeastern University, Boston. He served over 2 years at the US Department of Energy managing the flagship theoretical condensed matter physics program from 2008 to 10. He is a fellow of American Physics Society, the founding director of Northeastern University's Quantum Material Institute, an academic editor of the International Journal of Physics and Chemistry of Solids from 1994, and the founding director of NU's Advanced Scientific Computation Center. He served on various international committees and commissions. He has authored more than 400 technical articles and edited 17 volumes of conference proceedings covering a wide range of topics in condensed matter physics and material science, and written a major book on X-ray scattering. Professor Bunsel's group is constantly produced seminal advances at the forefront material physics for decades, including successful prediction of first topological materials and their electronic structures, spectroscopies, and application. He is a highly cited researcher at ISS Web of Science and Predictive Analytics since 2017. I am happy to be a part of Professor Arun Bansil's team for long. And with these words to Professor Arun Bansil, I remind all the participants to write their question in the chat box during the talk, which we can take, and at the end, when you can also unmute yourself and ask your question. With these words, I invite Professor Bansil to deliver his talk on topological quantum phases, novel superconductor, and ultra-thin films beyond graphene. Thanks, Professor Bansil.
Thank you. Oh, yeah, go ahead.
Yeah. So sorry, let me share my screen. Okay. Yeah.
Well, thank you. Thank you very much, Bahadur, for these kind words. I'm delighted to be here. And let me also thank Dr. Rai for organizing this meeting and for inviting me. I have not visited Mizoram, but I looked over the web. It seems to me it's a charming place, and I hope that I will have an opportunity to visit it one of these years. Now, we work on many things, but I thought that, qubits and Josephson junctions and optoelectronic properties and so on. But what I thought was I will focus on a message that, oh, next slide, yeah, thank you. Which, even though now it is kind of getting known, but it really hasn't fully been understood by people, by the community at large. So I want to focus on this message, and then of course I'll make some comments on other things as well. So here is the main point that I hope you will take away with you from this talk. For many decades now, the predictive capabilities, and the focus is on the word predictive, of this band theory paradigm that has now become very pervasive. And these predictive capabilities have more or less remained unchanged. Now, this is not to say that, we can do much bigger unit cells, we can do them faster, and all kinds of technical developments. But the heart of the ultimate reach of the band theory paradigm is the underlying exchange correlational functional. So unless you change that in some way, the capabilities of the theory remain limited. And that is the sense in which I meant that there really hasn't been any fundamental change in the underlying functionals for many decades. And by that, there are entire classes of materials that have remained more or less outside the scope of the first principles predictive abilities. And the cuprates are a classic example about which I'll say a lot more in a moment. So the message I hope you will take away and you will see is that this reach of the theory has now taken a next step in the last few years. with a new generation of exchange correlational functionals that have come online. And as a result, it is generating, it is spurring a new generation of predictive capabilities. And this has implications for all kinds of materials, topological, non-topological, and everything else. And that is what I hope I'll convey to you more clearly. Now, I want to emphasize up front that when it comes to condensed matter systems, which really are systems with essentially infinite degrees of freedom, there is never going to be a magic bullet that will capture everything. And there will always remain room in condensed matter sciences, material sciences, for many different approaches that will capture some parts of the properties of the materials better than others. But you will never be able to get everything right with one go, not at least in my lifetime, I don't think. So I just want to mention that up front. Next slide. So with that, I will focus on the cuprates quite a bit, and then I will say a few words about topological materials and spectroscopies. I want to also say a few words about alpha manganese and 2D ultra-thin films, etc., and then a few concluding remarks. Next slide. I have been very fortunate to have a wonderful group of people to work with, and the theory collaborators are listed here, some of the people that we are working closely with. Because of time, let me not introduce everybody, except at least mention a few of the people who are at this meeting. Bahadur Singh, of course, is chairing this session. You will be hearing Hasnain Hafiz, I think, later in the meeting. Sugata Chowdhury, maybe you have already heard him yesterday, I don't remember now. Tyrone, I think I saw him earlier, and also Amit Agarwal. I hope I haven't missed anybody, but at least I wanted to call out the people who are present here or will be present. We have also been very fortunate to have many experimental collaborations, but because of time, let me not go into details. Of course, we'll cite things as I go along. Next slide. So let me get to this matter of the high TCs. Now, it's a long-standing problem. Very soon after the discovery of the cuprate superconductors back in the 87, 88 timeframe, it was very quickly realized that the standard band theory paradigm will simply not work. It gives the half-filled material to be an insulator instead of to be a metal instead of an insulator. And there really isn't a whole lot you can do about it other than to start putting uncontrolled parameters such as the Hubbard U and so on. But once you do that, then your predictive power is very limited because what do you do as a function of doping, or if you have number of layers changed or what have you. So that has been the situation for a very long time. And what I will show you in a moment is that this new generation of functionals, in particular the so-called SCAN functional, which is an acronym, and I'll explain in a moment what that is, allows significant progress. And I'll particularly focus on the example of lanthanum strontium copper oxide, which is the original superconductor for which the Nobel Prize was given. Now, this stuff has been published in many papers, some of which are listed here, but there are more, and you can find those easily these days by going online. Next slide. So the SCAN functional, it's an acronym. SCAN stands for strongly constrained and appropriately normed. It's a meta-GGA class of density functionals. Now, for those of you who don't know what a meta-GGA, don't worry about it. You probably are familiar with the more common one, which goes under the name of GGA. And what is the variational freedom in a GGA type of a functional is that it has both the density and the gradient of the density that is allowed to vary. What happens in a meta-GGA is that in addition to the density and the gradient, you also have the kinetic energy, which is also the second derivative of the density. So it is this variational freedom that gives it the additional power, if you like. And within these meta-GGA, and if there are many such meta-GGAs, the scan functional is the unique one because it is guaranteed to satisfy all known 17 constraints that a meta-GGA can possibly satisfy. And these are, things like bounds, limits, norms. Like for instance, an exchange correlation hole must have half an electron in it and that kind of thing. So the details are not so important. The key point is that by these scan functional, one is able to much better capture diverse types of bonds, and there's quite overwhelming evidence at this point. And the functional is flexible enough to capture transitions between ionic, covalent, and metallic bondings. Remember that in a real material, you don't have strictly an ionic or a covalent or a metallic bond, but instead the electronic states, and within the same material, you can have different types of bondings for different electronic states, and these can also change from portion to portion of the unit cell. Now, for those of you who have been around, when it comes to condensed matter systems, we can make up all the stories that we want to about a functional, but in the end, the proof of the pudding, as they say, is in the eating. And in this case, it turns out that it actually does quite well. Next slide. So here is how this plays out. For the lanthanum copper oxide, the half-filled parent compound of the LSCO superconductor, if we have the LSDA or PBE, we get a metal. And you see that in the top panel, and the second one in the middle. Just focus on the solid line. Rest is not so important. And you can see that at the Fermi energy, you have finite density of states in LSDA as well as in PBE. The PBE seems to depress the density of states a bit, but nevertheless, it is still a metal. But when we go to scan, you see here in the bottom panel, it opens up a gap of about 1 eV. And this gap is opened up not by hand. It is, there is no U or anything put in. This is just the way the functional, there's no material dependence in this functional. And the gap that is obtained is about the size of the gap that is expected from experiments, optical experiments. Now, excuse me. Now, there are many issues exactly what the optical gap should be compared with and so on that I don't want to get into, except to note that for the generalized cone sham type of a theory, which is what a meta-GGA is, in fact, the fundamental gap, aside from excitonic effects, is in fact the optical gap. These are Koopman types of arguments that are not so important for us. Next slide. Now, one can coax the half-filled system into becoming an insulator by various ways. You can use hybrid functions, you can use U and do other things. But what happens is that if you do that, then you still get into trouble in not being able to produce the metal insulator transition with doping. But this particular functional, on the other hand, has no trouble doing finding that transition. So here you see on the left-hand side, the pristine half-filled compound, which has a nice big 1 eV gap, and that is the insulator. But when we dope it, then you see here the Fermi energy lies within the bands, and it is a perfectly fine metal. And this is rather important, not just for this system, but for many other situations, because there's a subtle change in the correlations involved when we go through metal insulator transitions, say under pressure and so on. And those have been pretty much outside the scope of these types of modeling or predictive modeling. This, of course, then means that that should be much better to do. Next slide. Another thing we can do, which is impossible to do unless you have a parameter-free theory, is to look at the energetics of different phases. So, you can't compare one phase with another if you have a parameter in there, because what value of parameter do you use? So what value of U will you use for one phase versus the other? But since I have no parameters, I can do that. And so we have compared the energies of the three well-known common phases of the LCO, high temperature tetragonal on the left side, and then the low temperature orthogonal and the low temperature tetragonal. These phases mainly differ in the way these copper oxygen octahedra are tilted and that kind of thing. These values of the energies of these phases that are shown here are very close to what's experimentally found. In particular, this very subtle difference of just a few MeV per copper oxygen plane, I think, between the LTO and LTT is also captured correctly. So this is a pretty impressive kind of a thing. Next slide. Now, once you have a first principles theory, and here, don't worry about the left-hand side, just ignore it for the moment. The right-hand one, I don't obviously expect you to see all these detailed colors and so on. The only thing I want you to notice, and these are different components of the density of states projected on various orbitals of copper and oxygen and so on. The interesting thing that I think you can already see is that notice the top of the copper oxygen band, that is pretty much as you expect, copper oxygen type, copper dx square minus y square with oxygen pxpy's. But the bottom of the band is not. So you see the bottom of the band, you see all these colors floating around. So you have admixtures of copper S, you have oxygen PZ, and the whole 9 yards. And what that means in simple terms is that the basic model of the cuprates that has now been used for who knows how many thousands of papers is fundamentally limited because it's a one-band model. And here you see that that is simply not the case. There is an admixture of other orbitals involved. And these things play an important role as you start putting under pressure things and so on. Now, we of course have a, excuse me, we of course have a full model, full first principles calculation. We can project it onto any other effective model, say one band model or three band or five band or what have you. And for example, if we do project it onto a one band model, then in fact the effective U values we get are quite close to what you would normally expect for such integrals, not the value of about 2 EV that is usually used, for just as a parameter in these calculations, many calculations. Next slide, Bahadur. Now, we were quite impressed with these results, and I actually didn't believe them for a long time. But at some point we checked everything we could, and things stayed quite robust. So we thought we would have a closer look at the magnetic structure, which is generally a very delicate thing. Getting magnetic structure right in anything, even these days, is not straightforward or common. But in this case, actually, we get the magnetic structure also very well. The predicted moment on copper that we find is about half a Bohr magneton, and that is very close to the experimental value. There is no moment on there's very small moment on the apical oxygens, 0.01 Bohr magneton. And the in-plane oxygens, and I'll say a few words on that in a moment again, they have no net moment but they're highly polarized, and you'll see in a moment that makes sense. Very interestingly, we are actually able to get the AFM ordering in which the locking of the spin direction with the lattice is correctly reproduced. That is along 45 degrees to the copper-oxygen copper bonds. And for this, you have to put in spin-orbit coupling. And as far as I know, that has never been possible before. Also, of course, this is indicating that you do need to include spin-orbit coupling effects for many purposes. We are also able to get the magnetic exchange energy correctly, which is a very delicate quantity. So calculated value of J is minus 138 MeV, whereas the experimental value is minus 133 MeV. And therefore, we would expect that we will reproduce the spin wave spectrum reasonably. Next slide. So I mentioned the magnetic moments and the magnetic form factors. And here, there has been a lot of analysis of the magnetic structures, and the way the magnetic moments are derived depend to some extent on what kind of a magnetic form factor one uses in analyzing the neutron data. But here we actually don't make any assumptions whatsoever. We just calculate the momentum density and the spin density. And therefore it should allow tighter limits on the form factors of the moments. And very interestingly, as I mentioned already, and it is not surprising, you have this large moment on copper sitting, and a couple of angstrom further away from it is an oxygen atom. So it's not at all surprising that it will be polarized, quite heavily polarized, but the net moment is zero, it turns out. The whole moment magnetization has the form of a quadrupole form. And this probably requires reanalyzing many things. Next slide. So let me summarize everything I have said so far. So this functional has predicted without any free parameters, no U, in a totally first principles manner, no different than what you would do in copper, for instance, metallic copper. The electronic and geometric structure, I didn't go into the geometric structure, but actually the geometric structure also is reproduced quite well. The energetics I talked about, band gap, magnetic structure, and I think it's fair to say that this is quite wide-ranging coordinate experiments. Now, as a theorist, the first thing you worry when a theory agrees with experiment in something is whether it's an accident or is it something more robust. Well, it is very clear that this is not an accident. We have looked at many other cuprates, 2212, IBCO, layer dependencies in mercury and thallium compounds, CCOC, iridates, and everywhere things seem to be working out quite well. Iridates where, for years, our group included, we have adjusted the strengths of the spin orbit coupling or added values of U to, mimic something or the other. We don't need any of that. It more or less is first principles. And that means, of course, that issues of what kind of topological states might be in a real material and so on can be analyzed quite clearly. Now, there's a whole set of issues related to the fundamental meaning of band theory and these energy bands and so on, which I don't want to get into here. But let me just say that the cone sham orbitals are not quasi-particles. They're not physical quantities really. And there is no intrinsic reason for the band theory plots have to do anything with real life. But the reality is that they do. And for instance, almost everything for new topological materials has been based on just using these plots. And so in some way they capture something real. And so, one can't just ignore it anymore. Next slide. Now, given these interesting results, we decided to go even further, and we decided to look at the stripe and magnetic phases in YbCO6 and YbCO7. Everything I'm going to say in the next 5-6 slides is contained more or less in this PNAS article. So we chose these two compounds because YbCO6 is a half-filled AFM insulator,